Okay, one of the things I wanted to talk about is implicit differentiation. That's definitely going to be on the test. It's going to be on the final exam. And it is a matter of, I'm going to switch over to my iPad, and so we can view that. One of the things I like to start with is talking about when you've got a function that's in terms totally of x, like we've typically done with polynomials, and you take the derivative of it, that is explicit differentiation. It's explicitly, you're taking the derivative with respect to x, and every term's in x, so therefore you take the derivative of each term. There's no y's over there to have to deal with. And so taking the derivative of this function with respect to x would be take the derivative of each term with respect to x. And you could write d dx of each term, okay? One way to write that would be to say, d dx of this polynomial, but that's what we typically do. So and then you could break it up and take the derivative with respect to x of each term and show that. You don't have to do that, okay? But the idea is that this turns out to be that dy dx then, and that's what we're shooting for, and when we're doing implicit differentiation, is equal to 2x plus 3. If you take the derivative of each term, that's what you end up with. All right, let's go to a different problem where we've got some other functions where y and x are both included in the function. So something like this, x squared plus y squared equals 4. I use the word function there, pardon the language there. But I use the term function, and this really isn't a function, What is this the graph of? This is a circle, It's a circle of radius how long? How long? So it's x squared plus y squared equals r squared. And in this case, r is equal to 2. So this is a circle of radius 2. So, and by looking at that, is this a function? Does it pass the vertical line test? No. As a result, this is not a function. And but it is the standard form for the circle, if you recall, is if we got the origin going there as the center, that's part of it. And it's r squared on the far side. So that turns out to be r. And the center of the circle, I'll show you a couple of examples of a circle that's off center. And that's a little more complicated situation you got to contend with. But what we're dealing with right now is we've got a circle, and it's not a function. So we don't use the word function for it, but you can take implicit differentiation to find the slope of the tangent line at any point of that graph. Remember, that's what we're finding. The question you typically is asked, find dy dx. What is dy over dx? So find dy dx, which will be the slope of the tangent line at any point on that circle. It's kind of a cool little moment. All right, but now here's the situation you've got to do. So what we've got to do, first of all, we're going to take dy dx, and like I did up here, up this situation right here, you take the derivative with respect to x of every term up there, okay? So I started by taking d dx of y, which is right here. That ended up being dy dx. That's what that turned out to be. And then I took the derivative with respect to x of this side, okay? Which, if you really split it up mathematically, I'm taking the derivative with respect to x of each term. So that's what you've got to do here. You take the derivative with respect to x of each term. And at first, you may want to write that out. So what we'd be doing here is the derivative with respect to x of x squared plus the derivative with respect to x of y squared equals the derivative with respect to x of 4. All right? And just like it happened up here, when you got the derivative with respect to a constant, that's equal to 0. So that's going to be going away. But if you've got a term that's just x's, then this first term, the derivative with respect to x that's 2x. Okay, now, this is where implicit differentiation takes place. We've got a term with a y in it, all right? And therefore, remember, this function's got all the x's are going on, is what we've typically done. If, with respect to x, that's what we're talking about. Well, y has got to be, you got to take a derivative of that also, okay? but with respect to x. So that means one of the important facts about the situation is that you are to say your y is it's a function. Y is a function in terms of x. Okay, so so the situation is that the independent variable x, y is a function in terms of the independent variable x. So that means if we take the derivative of a y term, you got to use the chain rule, because it's not just y, it's a function's inside there. You know, y is representing a function. So to take the derivative of respect to x, you've got to use the chain rule on it. And I'll show you that right now. So the idea is, remember, the derivative of respect to x, when you've got another term, it's a composite function, y has x's in it, all right? Then that means we got to take the derivative of the outside function and then multiply that, and then multiply times the derivative of the inside function, all right? So in this case, the derivative of the outside function, we've got y squared. The derivative of the outside function is 2y. That's the derivative of the outside function. And then we got to take the derivative of the inside function, which is y. So we get a dy dx. That's the derivative with respect to x of y. Notice, and I'll talk about that a little bit more in a second. But no, yeah, go back and notice how many y's are in this function. There's just one. That indicates that there's just going to be one dy dx when you're finished what we're doing right now. There's one dy dx. If there's one y, however many y's there are, that's how many dy dx's there's going to be. Okay. And then the last thing we've got to do is, what's the derivative with respect to x of 4? 0. So now it's a matter of solving. The goal was to find dy dx. So we're going to solve for dy dx. We subtract 2x from each side. Negative 2x. And then we divide by 2x. By 2y, excuse me. Divide by 2y. And then notice we've got 2's common. So it ends up being that dy dx turns out to be negative x over y. All right? Negative x over y. So any point on that circle, if you find the coordinates of that point, you will have the slope of that tangent line at that point. And the real obvious ones are up here. We have the radius of 2. So this is at the point 0, 2. Notice what the slope of the tangent line is here. The slope of the tangent line. The coordinate is 0, 2. So the coordinate of that, so the slope at that point of that tangent line is going to be equal to, at 0, 2, the slope is going to equal to negative 0 over 2, which is 0. The slope is 0. Same thing would be true down at 0, negative 2. And notice what would happen here at 2, 0. At the point 2, 0. You got negative x over y. So at 2, 0, the slope is equal to x. X is 2, negative x, excuse me. X is 2, and y is 0. So the slope is undefined. The slope is undefined when it's vertical down that kind of a line, okay? So you plug in the coordinates, both the x and the y, to determine what the slope is at that point. I tell you what, one other problem I'd like to show you, and let's do right now, is let's do the coordinates. I know this is going to be a little bit garbled here, but I'll hit it. If we find the slope of the tangent line right there at 45 degrees, that's pi over 4, okay? On the unit circle, this is pi over 2, and half of that is pi over 4. So at this angle right here, on that circle, it's pi over 4. Notice what the slope of the tangent line is. Notice, remember, the slope of this tangent line right here, tell you what, let's bring it down here to this side. No, we're going to stay up here with pi over 4. We're at pi over 4. That's what we're going to do. This angle right here is pi over 4. That angle right there is pi over 4. And we want to find what the slope of the tangent line is right there. Well, can you tell what it's going to be? The x and the y at pi over 4, which is 45 degrees. Remember, on the unit circle, it's square root of 2 over 2, square root of 2 over 2. But on our circle, since the radius is 2, it's going to be twice as big. And as a result, we got square root of 2 over 2 times 2. So the coordinates of this point right here are going to be square root of 2 and square root of 2. All right? So what is the slope of this tangent line at that point? Well, m is going to be equal to negative x over y is what we got. And that indicates, in our case, it's going to be square root of 2 and square root of 2. Therefore, it's going to be exactly the same, negative square root of 2 over square root of 2, which is going to be negative 1. So the slope of this tangent line right here is negative 1. Notice what it would be over here at 45 degrees over here, the 45-degree angle over here, which is what? That's pi over 4, pi over 2, 3 pi over 4, which is what, 90 and 45, 135 degrees? At 3 pi over 4, we've got one of the values is negative. You know, the cosine is negative. So in this case, it's still going to be negative x over y, but the answer is going to be positive 1. The slope is positive 1 here, positive 1 here, negative 1 here, negative 1 here. So that's using it on the picture itself and actually seeing what the actual value is. Okay? Questions specifically on that anywhere? I'm going to do another example of an implicit a function that requires implicit differentiation. Okay, all set? Okay, let's go to a new graph. I'm going to go to another one here. And let's do, here's a second one I'd like to do, which is a little more convoluted. And it is this, y to the third minus xy equals negative 6. One thing that implicit differentiation requires is you got to have the chain rule, like I said a little while ago. And then like in this case, you got to have the product rule. Look at that second term. We're multiplying x and y. Therefore, you've got to use the product rule. You got to use the chain rule because there's y's in there. And those are in terms of x. And notice this. How many y's do we have this time? We've got one here and we've got one here. So that means there's going to be 2 dy dx's that show up. And we've got a product rule here, all right? So don't let me get confused about, I'm going to just say if y equals, if I'm going to say if the function we're working with, if, I'm going to call it y. If y equals f times g, then y prime using, well, we got to use the product rule. I got f prime g plus f g prime. That's a different y than we're working with in there, but that's how we've typically been writing this rule out. So I wanted to have up there, I'm going to use the product rule on that second term, make sure I have that somewhere so I can see it and go with it, okay? Be solid on it. Okay, so now let's use implicit differentiation. The goal again is to find dy dx. And we're going to take a look on Desmos. One thing you can do on Desmos is you can graph this function on Desmos. You can't do it on your calculator because it's convoluted and it's not, it's not a function. I use the word function again. It's not a function because it doesn't pass the vertical line test everywhere. I'll show you that in just a minute. Let's take the derivative of this now. So we've got y cubed minus xy equals negative 6. We're finding dy dx. So take the derivative. I'm going to take the derivative of, so I'm going to take the derivative of each term. I'm going to write that out first. There's a shortcut way you guys can use also. If you're downstream, and that you can use y prime, instead of dy dx. Right now, we're actually looking for dy dx, so I want to make sure you get that in your head before I say you can use y prime for that. But so right now, I'm taking the derivative with respect to x of each term. And the first term, I got to use the chain rule on because there's a y in it, all right? So what do I get? I take the derivative of the outside, which is 3y squared, times the derivative of the inside function, which is y, which means I've got dy dx. 1 dy dx for that term. Okay, and now notice I moved the minus sign outside. You can do it either way. You can take the derivative of a negative function, but I just took the negative out. You got to remember that negative is out there. So it's going to be on our whole answer. When you do dy dx, you get two terms. I mean, when you got x times y, it's a product. You got to use the product rule. You're going to have two things that come from that. And that minus sign out front has to apply to both of them, okay? So you got to make sure you remember that and use parentheses around your final solution when you plug it back in. So we've got the derivative. I'll get the minus sign here. Now the derivative of this next term, xy, is I take the derivative of f, the first, times the second. So the derivative of x is 1 times the second, which is y, plus I've got the first, which is x, times the derivative of the second, which is y. The derivative of y is 1 dy dx. Notice the only place that dy dx showed up, there just showed up one time, and it showed up where it was g prime in our product rule. That's the only place dy dx shows up, is when you're taking the derivative of the y term. That's where dy dx shows up, okay? And then we'll move on, keep moving. The derivative of a constant is 0. So let's distribute this minus sign now and clean this up. And you can do several things. I'm slowing down and showing each step meticulously. I'm sure that you can do that more efficiently once you get it down better. But I'm going to do minus y minus x dy dx. And that equals 0. And now I'm going to solve. The goal is to find dy dx. Therefore, I'm going to get them on one side, get everything else on the other, factor out the dy dx, and then divide by what's left, okay? I'll say that again in a second. So the idea is, let's get rid of that minus y. So we've got 3, and I could do this all at once, but I'm going to do one step at a time here. Minus x dy dx, and add y to each side. So I've got y over on the other side. Now I'm going to factor out the dy dx. And again, when you get efficient, I could have done that in the previous step too, but that can get confusing when you do too many things in one step. And when you're just learning it, I'm trying to make sure you get it solid. So factor out the dy dx. Take the dy dx, and what's left? 3y squared, and I've got minus x, okay? And that equals y. And now, typically you multiply this back out and make sure you get what you started with, you know, when you're doing this problem. That would be good. Now I'm getting dy dx. This is a product, so that means I need to divide by what's in parentheses. So I end up with dy dx equals, y is on top now, and 3y squared minus x is on the denominator. That, you guys, is the slope for any point on this graph. The graph of this. Well, what does the graph look like? Tell you what, I'm going to go ahead and show it to you on Desmos. So I'm going to do that now. But the answer to the question, find dy dx, that's the answer. Now, one thing that's asked in a question that comes up somewhere, I remember where I took this problem, it said, find what dy dx is. What's the slope of the tangent line at 7, 2? Okay, first of all, check and make sure 7, 2 works there. And you see that that's y, so that's 8. 8 minus 7 times 2, 8 minus 14, that's negative 6. Yeah, that works. That's a point on the graph. Let's look on Desmos and see what this thing looks like. Okay. I had it up a minute ago and it is gone. And so I will do it again here. Get Desmos up here and go to that. Okay, and now I go to Desmos. And you'll check this out, you guys. What I did before, previously, was the first question we did was x squared plus y squared equals 4. Notice that on Desmos, you can draw circles. Look at this. You know, on your TI, you can't do that. On your Texas Instrument calculator, you can't. But on Desmos, you can draw that circle. And I solved the problem what the tangent line was. But what I want to show you right now is let's get off that. I want to show you what the function we just drew was, we just calculated with, took the derivative of. Okay? Look at this. This is not a function. It doesn't pass the vertical line test for most of it. Parts of it did, but this is the graph of y cubed minus xy equals -6. And notice at 7, 2, we got a part of the circle, part of the graph, okay? And what is the equation? That's the tangent line there. So what you do is you plug in, you can see, you plug 7, 2 into the function, into this function that we finished up with down here, and we end up with dy dx is equal to y is 2 over 3, 2 squared minus 7. And that gives us 2 over 4 times 3 is 12 minus 7. So that's 2/5, which is equal to 0.4. Okay? And then if you plug it into the function, you end up calculating b. You can calculate b. So we've got our xy. Let's go ahead and just do that real quickly. Y equals mx plus b. Y is 2. M is 0.4. X is 7 plus b. Now we end up with 2 equals 2.8. That's 28 with decimal point moved over plus b. And now if I subtract 2.8, I get b equals -0.8. So I end up with y equals 0.4x minus 0.8. And if you notice, I already have that on Desmos. And if you draw that line, y equals -0.4 minus 0.8. Sorry, I wrote that on a paper and you weren't watching, but I get it. And you can see that the graph is tangent and it touches at the point 7, 2, right? You can zoom in and verify that it's crossing right at 7, 2 and going on that kind of line. Okay, but that's the idea, slope of the tangent line at function. It's not a function. This is not a function because it doesn't pass the vertical line test, okay? So it is a relationship between x and y, and it's a graphable type scenario. Questions at all about that situation? I will ask you on the test, give you a function of a circle or a function of this other. I tell you what, one other thing I want to look at, I got up on the calculator here. I'm going to also do a new share. And this time I want to go to the book. I've got something up here on the book that is actually a couple of graphs. Let me go to, okay, I tell you what. It's just how graphs of circles, hyperbolas, ellipses, circles, graphs of tangent lines are going to be consistent with those things. Let me do a new share and get that book up here. So I'm going to go to the Zoom. I'm going to go to here, and that will let me pick the book real quick here and take a look at the graph in section 5.2. Okay, not going to do that. Okay, so here's the situation. We'll talk about that another day, but stop and look up, equations of a circle. A minus sign in between instead of a plus sign between x squared and y squared would be a hyperbola. Curves going away from each other. An ellipse, if x squared over 4 plus y squared over 1, that's being stretched one way more than another. That turns out to be, an ellipse in a very certain sense. If you have coefficient, and if you can have an off-center circle too. It's off the center of this is on the origin, okay? This is x minus 0 and y minus 0 are the center of this function. Well, if that was x minus 2 and y minus 3, then you'd be at the center of 2, 3, okay? And your center would be there with a radius 2, and that would be a different situation. All right, what I want to do now, any other questions about that at all? Okay, let's go back to, I want to go to talking about the gravity problem, gravity type situation, all right? This type of problem, I'm going to go back to my iPad. And show you something here that is got to do with a gravity-related problem. Okay, and here's a situation where we have a graph of a function, and this isn't a perfect drawing because notice what the shape of this graph is. I'm giving you this function. We're going to build up to this and talk about this more when we get to antiderivatives and things. But I want you to see this. S of t is called the position function. How high is an item above the ground at a given time t? Okay, at a time t. And if you notice the shape of this, what is the shape of this graph? Notice what is the function? It is a t squared. That's x squared. That is a parabola, okay? And notice it's upside down. So a better, more accurate drawing of this would have been, because this is driven over time, a more accurate drawing would have been to have it continue going out like that. Not like it does in life where it comes straight down or after a certain point, etc. What we've got going is this is time on this axis, the x-axis, and this is the position, how high it is above the ground up here, all right? Well, notice how high it is above the ground, and at this time, this is saying you are 48 feet above the ground when you're starting. This turns out to be negative 16t squared. I'll give you this on formula sheets that we're dealing with, plus the initial velocity, however fast it's going when it leaves the hand or whatever is propelling it. And this is how high it is when it starts off the ground, all right? So the idea is, this is how high it is above the ground, S of t, at any time t. Notice at time 0, we're starting here, you plug in t equals 0, and you end up with 48, all right? You plug in 0 for t, S of 0 equals 48. So we are 48 feet above the ground at time 0, at top of this building, whatever the thing is, all right? Now, one point I want to make is, you throw the thing up into the air. How high does it get? How long is it before it reaches its peak? Okay, well, this is an inverted parabola. And notice that what happens, the rate of change of the position is how fast is that thing moving up or down, okay? So how fast is it moving up when it leaves my hand? Well, according to this function, it was 32 feet per second. This is in feet, and this is feet per second. That's the initial velocity. And I made multiples of 16 nicely to fit this function so that it'll work out nicely. But notice the rate of change is the derivative. If I take the derivative of S of t, I'm finding how fast the position's changing. And that is how fast it's changing is how fast is it moving, which is velocity. So it turns out that if I take S prime of t, the derivative, I'm actually determining the velocity of that item that's in my hand that I just threw. And now if I take the derivative of this, look, if I take the derivative of S of t, bring the 2 down front times negative 16, I've got negative 32 t to the first, and then take the derivative of the second term, I get plus 32. So, and then I take the derivative of 48, I get 0. So it turns out that this is the velocity function. At any time t, that is how fast the item is moving. So notice now, one thing I want to say is that also when the one thing that is a fact of physics, when it's moving away from moving up, we call that positive direction. When it's coming down, it's negative direction. That means somewhere in between it hits 0. And where the slope is 0, the slope of that tangent line, the derivative of the function set equal to 0 is going to tell us what t causes that to be equal to 0. So we've got negative 32t plus 32 equals 0. That's 32t equals 32. T equals 1. I picked numbers that worked wonderfully, you know, so it's an integer. Typically, it's not exact like that. But at 1 second, this was 0 on top of the building. At 1, we reached the peak. A question I will be asking you on the test is, how long will it take to reach the peak? Take the derivative, set it equal to 0. Now, what's the height? How high did it get? Well, the position function is s of t. How long did it take to get there? 1 second. Plug 1 into s, and you've got how high it got. So s of 1 equals negative 16t squared plus 32t plus 48 is equal to negative 16 plus 32 plus 48. That's 80 minus 16. That's 64. So the answer, how high did it get, is 64 feet. That is it. How long did it take to reach the highest point? 1 second. And part of the answer is the increment. So it took 1 second to get there. Another piece that's coming, and we'll do this a little bit downstream too, but how long did it take to hit the ground? Okay. Notice this also. Notice this, that it's a parabola, therefore it's symmetrical. Therefore, this matches this. So it'll get here. It took 1 second to get here. It's going to take another second to get here. Okay? And then let's see. So the idea now is, when does it hit the ground? Could be another question we could ask. And that's kind of a fair game question. I'm thinking of, we'll practice this again tomorrow some, all right? But when will it hit the ground? And the idea is, what fact do we have when it hits the ground? The position, how high is it above the ground? It's 0. As a result, we've got the situation that the position function is equal to 0. And that is equal to negative 16t squared plus 32t plus 48. Now, you could do this algebraically. You can use the quadratic formula on the quadratic function. I picked numbers that factor nicely. Notice if we take out negative 16 here, we get t squared minus 2t minus 3. And I'm going to move over so we have a little room to write. Negative 16, that factors into t and t. Factors, a little explosive moment there. But we've got 3 and 1, and the middle term's got to be negative, so it turns out to be minus 3 and plus 1. So as a result, when does that happen? When does it hit the ground? Well, there's 2 different times it happens for this function. And we've got t minus 3 equals 0, so that's t equals 3. And we've got t plus 1 equals 0, that's t equals minus 1. Minus 1 doesn't make sense in our logic. So the correct answer would be, when does it hit the ground? T equals 3, that's 3 seconds. Notice where, and so this is at 3. Notice where minus 1 puts us. Minus 1 mathematically works, okay? It works, but it doesn't, you don't use that to answer the question. It shows that it really works. Minus 1 is a solution to this function, equal to 0. But the answer to the question is, when does it hit the ground? That's at 3 seconds.